Hello, welcome to another episode of distance learning class for grade 9 science. And we are still in the continuation of the chapter Simple Machine. And in Simple Machine, in last class, we were discussing about lever, one of the simple machines. So in last class, we discussed on mechanical advantage in three different types of lever. First class lever, second class lever, and third class lever. So how can we determine the mechanical advantage in first class or second class or third class lever? Now, let me make it more clear how we calculate or how we determine the mechanical advantage in different types of lever. For example, let's assume a lever to be an ideal one, a lever without any friction, frictionless lever. Let me draw a second class lever. Suppose load is here and we apply effort at this point. Now, if we move this lever in this direction, so it will get displaced this way. So this is our effort distance, and this is our load distance. This is load distance, and this is effort distance. And we are applying effort here, and our load lies here, and this is fulcrum. This is fulcrum. Now, if we assume this particular lever a frictionless one, I mean, suppose no friction acts here. Let's suppose this is an ideal one. So, efficiency here is MA upon VR times 100%. If we say this is an ideal one, efficiency is 100%. MA upon VR times 100%. It means what? It means MA equals to VR. MA equals to VR, right? So this shows in this lever, MA and VR, they are equal. Now, what is VR here in this lever? VR is effort distance to load distance. And here, see, effort distance is greater than the load distance in the second class lever. So this becomes greater than 1. I'll repeat it. In this particular lever, second class lever, this effort distance is greater than load distance. So, velocity ratio in this second class lever, it is greater than 1. So, it means this implies mechanical advantage is greater than 1. When VR is greater than 1 means M is also greater than 1. This is how in second class lever we get MA greater than 1. MA greater than 1. MA greater than 1 means what? M means what? MA is load to effort. This is greater than 1. This fraction is greater than 1 means what? Load is bigger than effort. Load is bigger than effort. See? Means in second class lever, effort that we apply here, it is always smaller than the resistance or the load that we are going to overcome. This is how second class lever always magnifies the effort applied. And in the same way, in third class lever, we apply effort at this point, suppose load lies at this point. Now, if it is, this lever is displaced, suppose, so this is our effort distance and this is our load distance. See, this is fulcrum. And in third class lever, wherever the effort be, here, 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 anywhere between fulcrum and lever, wherever the effort be, the effort distance, it is always smaller than the load distance. Effort distance, it is always smaller than the load distance. So here, velocity ratio, it is less than 1. It is always less than 1. So this implies MA is less than 1. MA is less than 1 is what? Load overcome, it is smaller than effort applied. So in third class lever, effort that we apply here, it is always bigger than the load we overcome. The effort that we apply here, it is always bigger than the load overcome, right? In last class also, I gave one example. Even while using a shovel for throwing a heap of sand from one place to another place, we use shovel, right? So while using shovel, see, shovel is third class lever. So while using shovel, effort that we're applying there, it is always greater than the amount or the weight of the sand we throw. But still we use it. Why? Because it speeds up our work. The main point why we use third class lever, even though it doesn't magnify the effort applied, the main point, the main reason is it speeds up our work. Next, definitely it helps us to do our work in a safer way. That's why we use third class lever, although it doesn't magnify the effort that we apply. So I want to show you some questions. So a few questions I mentioned here. Mechanical advantage may be greater than or equal to or less than 1 in first class lever. In first class lever, this is load, this is effort, and this is fulcrum. In first class lever, the mechanical advantage, in first class lever, the mechanical advantage, it may be equal to 1. Mechanical advantage may be equal to 1, or maybe greater than 1, or maybe less than 1. So what may be the reason for this? If this fulcrum is exactly in between load and effort, in that case, load distance and effort distance, these two are equal, so M is also equal to 1. See, if we assume this one, this particular machine to be an ideal one, MA and VR, they are equal. If we assume this particular device to be an ideal one, MA and VR are equal. Let's ignore the friction acting in the movable part or between the movable parts of the device. So this lever and fulcrum, so these two are movable at this point. So let's ignore the friction acting there. So if so, we can say MA and VR are equal. So when this is exactly at the middle, VR is equal to 1, this is equal to 1, right? So when this is slightly towards load, then VR is greater than 1. When it is slightly towards the load, effort distance becomes more than the load distance. So it is greater than 1. And when it is towards, when the fulcrum is towards the effort, in that case, effort distance becomes smaller than the load distance. So it is less than 1. So MA can be equal to 1, can be greater than 1, or less than 1 in first class lever. Whereas in second class lever, MA is always greater than 1. In second class lever, MA is always greater than 1. In second class lever, MA is always greater than 1. Because in second class lever, effort distance is always greater than load distance, due to which effort required to overcome the given load is always smaller than the load to be overcome. So MA is always greater than 1 in second class lever. Whereas in third class lever, in third class lever, effort distance, it is always smaller than the load distance. So the effort required to overcome the given load is always greater than the load to be overcome. So in third class lever, mechanical advantage is always less than 1. So I hope you understood why or how mechanical advantage is greater than 1, always greater than 1 in second class lever, always smaller than 1 in third class lever. Next simple machine is pulley. Now what a pulley is? What a pulley is? Pulley is simply a circular disc. It is a circular disc. Pulley is a circular disc which has a groove on its circumference pulley is a circular disc which has a groove on its circumference. So its rim or its circumference is not flat. This is not flat. It is grooved. It is grooved. Its circumference is grooved. Why? So that a rope or a string can be passed through it or over it. Now, in a pulley or through the groove of the pulley, a rope is passed to one end. In general case, to one end of the rope, we generally attach the load to be overcome, to be lifted up. And at the other end of the rope, we simply apply the effort. See? So, pulley is a circular disc. Pulley is a circular disc having groove on its circumference through which a rope is passed. This pulley can be metallic or wooden. This pulley can be metallic or wooden. So we get to see this pulley in different systems, devices. In a huge crane also we can see pulleys, number of pulleys being used there. So how this helps us to do our work, we will discuss slowly. And there are different types of pulleys. The one I have drawn here, it is called fixed single pulley. It has been fixed on a support. It is hanging on a support, and it hangs here on a horizontal axis, and it is free to rotate about that axis, and it should rotate. If it doesn't rotate, it doesn't work. So the friction acting between this pulley and the axis, if it is lesser, it becomes more efficient. So efficiency of a pulley depends upon how much friction acts here. Lesser the friction acting between the pulley and the axis, more is the efficiency of the pulley. Next pulley is single movable pulley. This is support. So in single movable pulley, one end of the rope is fixed, and we apply our effort at the other end, and here load is attached to the pulley itself. This is single movable pulley. Please ignore my drawing. This is fixed pulley, fixed single pulley. This is movable single pulleys. See the differences. Here, at one end of the rope, load is attached, and other end, effort is applied. And here, pulley is fixed to a horizontal support, whereas in single movable pulley, load is directly attached to the pulley. Here, the rope, one end of the rope is fixed, and effort is applied to the next end of the rope. Similarly, we can get to see mixed pulley, different pulley system having 2, 3, 4, 5, 6, many number of pulleys may be there in the system. So, as we increase the number of pulleys in a pulley system, its efficiency goes on increasing. It helps us to do the work with lesser effort. Its mechanical advantage goes on increasing. As we increase the number of pulleys, its velocity ratio increases, and as the velocity ratio increases, the effort required becomes lesser and lesser. For the same load, the amount of effort that we need to apply, it goes on becoming lesser and lesser as the number of pulleys is increased. So now, how to calculate velocity ratio in pulley? Now, for example, in this pulley, so if we need to lift it up by 1 meter, definitely it should be pulled down by 1 meter. If we need to lift it up by 1 meter, so this end of the rope should be pulled down by 1 meter. It means what? Effort distance and load distance, they are always equal. So VR equals to 1 in this single fixed pulley. Now, in this single movable pulley, how do we calculate? How do we know the VR here? If this load is to be pulled up by suppose 1 meter, what happens? This section of the rope, it should also get pulled by 1 meter. This section of the rope should also get pulled by 1 meter. It should get pulled by 1 meter from both the sides. But from this side, we cannot pull it. We can pull it only from this side. We can apply effort from only this side, only from this side. So what happens? To pull it up by 1 meter, now we need to pull it up by 2 meters. See? I would repeat it. To move it, to pull it up by 1 meter, this section of rope and this section of rope, both the sections of rope should decrease by 1 meter. Means they should get pulled up by 1 meter. But we cannot pull it up from this side. We can pull it up only from this side. So what happens? So from this portion of the rope, from this section of the rope here, the whole 2 meters should be pulled from this section of the rope. So to pull it up by 1 meter, we should pull it up by 2 meters. So just double. So here effort distance is just double of load distance. So VR is 2 here. VR is 2. Here VR is 1. Here VR is 2. Right? So which one is easier for us to use? Definitely single movable pulley. Why? If we assume these two devices, ideal one, frictionless, then MA goes to VR. So here MA equals to 1, here MA equals to 2. See? If these two devices are frictionless, suppose, then in first one, this fixed pulley, mechanical advantage is 1. In second one, in movable pulley, mechanical advantage is 2. So definitely it magnifies, the single movable pulley magnifies the effort applied. So this is better than the first one. But still we use it, although it does not magnify. In practice, definitely M is less than 1 here in practice, because here we have ignored the friction acting here. But in practice, there is friction. So because of this friction, definitely effort that we need to apply here becomes greater than the load. But still we use it. The reason? It helps us to change the direction of applied force. For example, you are going to pull a bucket of water from a well. So while pulling bucket of water from well, you need to apply force against the gravity. But using pulley, see, you are applying force in downwards direction, that is along the direction of gravity, and that is quite easier than using force or effort against the direction of gravity. So although we are using our effort in the direction of gravity, it is being pulled in upward direction, against the gravity. See, we are applying force in this direction or in downwards direction, but the load is being pulled in upward direction. So finally, it helps in changing the direction of the effort that we apply here. So although it does not magnify the effort applied, it helps us by changing the direction of the effort that we apply. So it is useful. Other system, combined system. Let me draw a pulley system where two pulleys are used. Compound pulley or combined pulley system. Compound or combined. See here, in this combined pulley system, here I have drawn two pulleys. So this is one end of the rope where we apply effort, and this rope goes down to the lower pulley, and from this lower pulley it goes up and gets attached here to the upper pulley. See here, and the load is attached to the lower pulley here. It is like a fixed pulley and a movable pulley combined together. So this is combined pulley system. Now see here, this is a framework. This is a framework where pulley is fixed, and pulley is here. Pulley is free to rotate about a horizontal axis. A horizontal axis is there, and a pulley is free to rotate about that axis. So there is framework, and at the lower point of the framework, the rope is attached, and this rope goes through the lower pulley, and it goes up again. It goes through the groove of the upper pulley, and finally to the next end of the rope we apply our effort. And similarly, to the framework of the lower pulley, to the lower end of the framework of lower pulley, load is attached. Now see here, to move it by 1 meter, to move it up by 1 meter, to move the load up by 1 meter, this section of the rope and this section of the rope both should get pulled up by 1 meter. From here also it should decrease by 1 meter, from here also it should decrease by 1 meter. To make it move up by 1 meter, this section of rope and this section of rope both should decrease by 1 meter, and for this we need to pull it down by 2 meter. Do you understand this point? To make the load move up by 1 meter, this section of rope and this section of rope both should get decreased, or both should decrease by 1 meter. So to make it short, and to make it short by 1 meter, we should pull the rope from here by 2 meters. It means what? The distance traveled by effort here, it is double the distance traveled by load. Always in this double pulley system, the distance traveled by effort is always double of the distance traveled by load. It means effort distance is always double of the load distance. So in case of this combined pulley system having two pulleys only, VR is 2. And if we assume this to be frictionless, MA is also 2. If we assume this simple machine to be frictionless, MA and VR, they are equal. So if we, now here what we can generalize is, this 2, it is equivalent to number of pulleys. So in a pulley system where a number of pulleys are there, what we can generalize is VR is equal to number of pulleys. VR is equal to number of pulleys, except in single movable pulley. In single movable pulley, there's only one pulley, but still VR is 2. So except that single movable pulley, in all other pulley systems, we can say VR equals to number of pulleys. So in this slide also you can see, in the 4 figures, in these 4 figures you can see, or you can find out VR. In first pulley VR is 1, in second pulley VR is 2, number of pulleys 2, in third pulley VR is 3, in fourth pulley VR is 4. So you can find out the efficiency of each pulley system here. So if you cannot catch up in this live class, later on you can go through the Facebook page of Kalika Television, and from there you can again visit the video, you can again watch the video and go to this lesson again and take the help. So I have brought some questions for you. Velocity ratio of a single movable pulley is 2. Why? I just explained why VR is 2 in single movable pulley. VR is 2 in single movable pulley because effort distance in single movable pulley, it is always double the load distance. So if we need to pull the load up by 1 meter, then we have to pull the rope down by 2 meters. It means effort distance always becomes double of the load distance. Similarly, a pulley system with 6 pulleys, number of pulleys is 6. That is used to lift a load of 600 Newton. Load is 600 Newton with the application of 120 Newton effort. Effort is 120 Newton. So find the efficiency. Efficiency is what? Number of pulleys is given, that is 6. So this is VR. VR is 6. Load is given 600 Newton. Effort is given 120 Newton. Now let's find out the efficiency of the pulley system. How to find out? Efficiency is MA by VR times 100%. MA, load to effort, right? VR as it is 100%. Now load and effort. Load how much? 600, effort 120. VR how much? 6. How much is it? 500 by 6%. It's 83 point something like this, 33%. This is the efficiency of this pulley system, where number of pulleys is 6, and to overcome, in this system, to overcome a load of 600 Newton, effort required is 120 Newton, right? So if such parameters are given, we can easily find out the efficiency of the particular pulley system, and it has come to be 83%, 83.33%. So this is how we can solve some numerical problems related to pulley system. Okay, dear students, I want to conclude today's class here, and you also try to solve such problems at home through your textbook or reference book, whatever you have at home. In next class, we will come up with the next topic or next type of simple machine. We still have 4 different simple machines left. We just finished lever and pulley. We still have wheel and axle, inclined plane, screw and wedge, and some other topics also in this chapter. We'll discuss in our next classes. So till then, have a good time, stay safe, stay inside. Thank you, bye-bye.